All right, welcome to the new normal for videos for Physics 221 for the remainder of the semester. This is how it'll be. My plan is to do a lot of short segments, trying not to keep any of these longer than 10 minutes, and using as many as I need to fill up the time to get the content that I want to discuss covered. Some of them might be a little longer than 10 minutes, but I'll do the best I can. All right, and this week you'll be doing a lab of building your own capacitor, which I'll actually be doing. You'll be watching me. And there is another homework that's available. Right now it's due Friday, April 3rd. So hopefully the content that you see here will be sufficient to help you with the homework. I'll be available if you have questions during class time. You don't have to watch this during class time, but during class time I'll be available at least 9 to 9:50, and then of course by email. Drop me an email if you have other questions. I'll get back to you. You can also call me, and my cell phone is on the 831-236-4987, but it's also on the syllabus, and I'll email it out. Okay, I'm going to get on to the content here. This is where we're at right before we left for the last lecture, and I want to just go through this and then go from here to talk about capacitors. Imagine you have two infinite plates. One's positive, one's negative. I'm going to draw them on the board. And I want you to sketch the electric field lines and lines of constant potential. So you can feel free to pause this and do it while I go to the board. Actually, I should do it. Make black negative and green positive. And the negative I have here to the left of the positive. I do red, but I don't have my red marker with me at the moment. All right, so electric field lines. They start on positive charges, they end on negative charges. And those can be charged planes or actual charges. When you have charged planes, these are supposed to represent planes of charge, not lines of charge. In that case, they're going to begin here and end there. And they're going to be what we call uniform. In other words, everywhere in the space in between here, the electric field is constant. And if you recall, the electric field has a value in between the two plates of the electric field charge density divided by the permittivity of free space. And we talked about that right before we left the lecture. I don't know if you can see that right here. That's the electric field strength is equal to that. The direction is equal to, in this case, minus I hat, or in the negative x direction. Great. So what are the lines of constant potential? One of the things I mentioned to you is that lines of constant potential will always be perpendicular to the electric field lines. So they're actually relatively straightforward to sketch here. They're parallel lines that look like this. Notice they're all perpendicular to the electric field lines. And what typically happens is we arbitrarily assign a potential to the negative plate. We say the potential on this one is 0, and the potential is going to increase as we get to the positive plate where it's going to be the maximum. Okay, so that's a little bit of a review. And you may say, what happened to the 2 here? Because it was sigma over 2 epsilon 0 when I just have a single plate. Electric field everywhere from a single plate, just to review, is sigma over 2 epsilon 0. And when you have two plates, one being positive, the other being negative, they're each going to contribute that amount. When you add them together, you get that for review. Okay. And on the next slide, what I have is just a summary of really everything we've talked about so far regarding the electric field strength and the potential associated with both a point charge, so dot in space where the charge is all located, and a plane of charge, or a positive plane of charge. And the one we probably talked about least is the one to the lower right, this one here, of what the potential is associated with a plane of charge. Basically, it's saying is the potential is linear as you go away from a plane of charge, or in between two planes of charges. If you go a certain distance x, and then another distance x, you'll increase by the same potential as you go away from that positive or negative plane of charge. So that's really what this is saying down here. And we're actually going to use this as we talk about capacitors. All right, so for the sake of review, I think we did this problem right before I ended the first half of the semester, so let's do it again. Let's find the electric field strength and direction at the location of the star on this PowerPoint slide. Go ahead and do it. Pause the video if you need to. I'm going to come over here and do it right over here. I have the drawing already set up. We already talked about the direction. The direction is going to be minus I hat. That's going to be the direction because it's in the negative x direction. So the strength of it at this point is going to be equal to sigma over epsilon 0. You may say, well, wait a second, this is a plus sigma, this is a negative sigma. Whenever I have two planes of charge, they're always going to have the same charge density. So kind of keep that in mind. This is going to be the electric field strength between them. So all I have to do is calculate this, and that's going to be the electric field strength at any point in between them. Not just at the center, but at any point in between the two planes of charge. So I gave you the charge density. I said that's equal to, I'm going to darken this. If I can do this right, it is there we go for the units. You can still see that on here. I hope so. It's Coulomb squared per Newton meter squared. That's the unit of this, of the permittivity of free space. When I do the math and divide them out, this comes up. And I'm going to pause this. I need my calculator for this. I'm not going to try to do it in my head right now. Okay, I got 1.13 times 10 to the 10th. I hope you got something like that too. So I'll put minus 1.13 times 10 to the 10th newtons per coulomb I hat. That is the strength of the electric field in between these two plates. You may say that looks like a huge number, and indeed it is. But look at that charge density. 0.1 coulombs per meter squared is a huge charge density, far more than you would generally expect. So you're going to get an enormous electric field between these two plates. And then the next question is, if the plates are separated by 0.1 millimeter, and the left plate has a potential of 0 volts, what's going to be the potential of the right plate, and what's going to be the potential of the star, the location of the star? So let's do that too. So how I would do that is, when the electric field is constant, or uniform I should say, when it's uniform, then you can calculate the potential in this fashion. You can say the potential is equal to the electric field times the distance from the point of zero potential. So at this point here, I'll say the potential is 0. So if I want to know what the potential is at the other plate, I need to know the distance. It's 0.1 millimeters from this plate. So I take this value of electric field, multiply it by 0.1 millimeters, and that's going to give me the potential at the right-hand side plate. So let's do it. And I think you can just still see me here. So if I multiply 1.13 times 10 to the 10th newtons per coulomb times 0.1 millimeters. I'm not going to worry about the sign of the electric field. That just tells me what direction it is. If this is 0, then it's going to get higher as I go up the hill to the positive charge here. So it's going to have to be a positive voltage between here and here. If I put my positive lead of my meter here, my negative one there, I'd register a positive voltage. That's the voltage I'm looking for. I have to convert millimeters to meters. So that's going to be 10 to the minus fourth meters. I'll write that over here. I'll say 0.1 millimeters is equal to 10 to the minus 4 meters. And the way I know that is that I know that there are 10 to the 1 meter is 10 to the third millimeters. Okay, so this is 10 to the minus 3 times 10 to the minus 1. I get 10 to the minus 4 meters. So I can replace the 0.1 millimeters with 10 to the minus 4 meters. Multiply this out, and I'm going to get 1.13 times 10 to the 6th Newton coulombs per meter. Now you may say, wait a second. Let's see, I'm sorry, Newton meters per coulomb. I apologize, Newton meters per coulomb. You may say, wait a second. This is supposed to be a potential. In the next video, I'm going to resolve that. Newton meter per coulomb. It's supposed to be in volts. What's going on? Hold on tight.